Hello everyone. In part 20, I have started Wittig reaction. Then the next part, that is 21, I have discussed stereoselectivity of Wittig reaction. And in this one, that is, it is actually the third part of Wittig reaction, we will see what is modified Wittig reaction. That is some changes in the conditions that can really modify the Wittig reaction. And it will be better if you watch the previous two videos before watching this. Okay, it will be easier for you to understand. You can find the link appearing on the screen. There will be basically two modifications. The first modification is known as Horner-Wittig reaction, which is an improved Wittig reaction. So in this Wittig reaction, what difference we have? Before beginning that, we have to see what is the disadvantage in the original Wittig reaction. In original Wittig reaction, there is production of phosphine oxide, which is actually the side product. So this is basically the fate of the Wittig reagent, that is the elide. Okay, so the phosphorus elide, that is ultimately transformed to phosphine oxide. Now this compound, it is very difficult to eliminate from the reaction because this is the side product. So when we will purify the actual desired product, then removal of this side product, that will create problem because this is not water soluble, first of all. Okay, and this is very polar. So when we will do column chromatography for purification, then also it will be really difficult to remove. So to remove this disadvantage, what we can do, the modified version, it allows for the removal of phosphorus as water soluble side product. So now instead of taking phosphorus elide, we will take some other compound of phosphorus, and as a result the side product that will be formed, that is the ultimate fate of this phosphorus compound, that will be water soluble and we can remove it very easily. Okay, so that is the purpose of this modified version. And this is known as Horner-Wittig reaction. So what difference we have here? This is the aldehyde or ketone, any of this, that is obviously required. And instead of elide, now we have phosphonate ester. Okay, so if we consider phosphoric acid, then you will be able to understand what is phosphonate ester. So here instead of OH we have ethyl group, that means it is ethyl ester. And here we have CH2, then electron withdrawing group. So there must be some presence of electron withdrawing group. Why it is necessary? Because we want these two hydrogens to be acidic in nature. Because ultimately we are using base, sodium hydride, which is very strong base, and it will remove this proton and there will be generation of carbonyl. Remember, in case of elide, we have negative charge over carbon already. But here we are generating this negative charge in the medium with the help of some strong base. So that is why this electron withdrawing group, it must be present, because if it is present, then the carbanion, that will be very stable. And here the side product, that is the, you can say the fate of this phosphonate ester, is this type of dialkyl phosphate salt. We have used sodium hydride, so that is why it is in sodium salt form. So as it is in salt form, it is very water soluble, and as a result, elimination of this side product, that will be very easier. So this is the modification. So the electron withdrawing groups that we can take is, it will be R, CO2R, then C double bond OR, it may be cyano, or SO2R, these type of groups. Okay, so this improved version, you can call it Wittig-Horner reaction, or sometimes the other names are also used. It employs phosphonate carbonyl because carbonyl will be generated ultimately at this carbon. Okay, and this carbonyl is generated from phosphonate ester. Now this is used instead of phosphonium elide. So what is phosphonium elide? That is in detail discussed in the original, that is the first video of Wittig, which is part 20. Please watch that. And there we have used, that is in the original Wittig reaction, phosphonium ylide, but now we are using this type of phosphonate carbonyl because the fate of this phosphorus compound, which is one of the reaction partner, ultimately it will be converted to water soluble salt, so that is why its removal will be very easy for us. It produces highly polar, that means water soluble dialkyl phosphonate salt, and it can be eliminated easily. But if we consider phosphonium ylide, then this type of phosphine oxide will be produced which is not water soluble, so its removal will be difficult. Now in this mechanism, that is in this reaction, what will be the mechanism? In the next slide we will see that. So we are using here sodium hydride, right? And in electron withdrawing group, what we have taken CO2R, that is CO2ET. So here these two hydrogens will be acidic in nature. In presence of NaH hydride, it will be acting as base and it will capture these hydrogens. So sodium hydride or this alkoxide anion, it may be used, not just sodium hydroxide, we can also take any alkoxide anion also. It may be used to deprotonate this ester so that we can get enolate type of anion. So here you can see this is actually carbanion, but here enolization is possible, right, by resonance. So that is why this will have some stability. These phosphonate carbanions are much more nucleophile than the less basic phosphonium ylide. So just remember, in original Wittig, where we have used phosphorus ylide, the carbanion that is produced, that will have less nucleophilic nature, but in this case this carbon will have more nucleophilic and less basic, and that is actually required. Here we want nucleophilicity, we do not want basicity. And what is the difference between nucleophilicity and basicity? Basicity means this is also negatively charged species, but it will be looking for some hydrogen, that is proton. But when we are calling it nucleophile, this is also electron rich species, but now it will attack some other atom which is electron deficient rather than hydrogen. And mostly in organic chemistry we always say that it is the carbon atom which it will attack. So we want the reagent to be more nucleophilic and less basic, and that is the case here. So this is a good thing. Okay, now this type of resonance is possible. These are the enolate type of anion, right? So this is one enolate, and if the that is negative charge is going towards right hand side, then another enolate is also possible. So because of this type of resonance structures, this carbanion, that is very stable. Now this enolate, it will react with the carbonyl compound, and this type of mechanism, it will attack this carbon, negative charge over oxygen. So now you can see a new bond is formed between these two carbon, and this is here in red color, negative charge over oxygen. Now this negative charge, now rest of the mechanism is you can find some similarity with the original Wittig reaction. There will be negative charge over oxygen. Okay, so this type of 4-member ring we have also seen in case of original Wittig reaction, and ultimately what will happen, there will be bond formation, that is another CC bond formation will take place. Okay, so PO double bond produced and CC double bond produced. So this is actually E-alkene. Now in case of Wittig, original Wittig, what we have seen, that we can either make E-alkene or Z-alkene, and that depends on the nature of the ylide, whether it is stable or not. Okay, so if it is stable, basically that will lead to E-alkene, but if it is not stable, that will lead to Z-alkene. But in this modified version, that is Wittig-Horner reaction, Wittig-Horner reaction, it gives exclusively E-alkene. Okay, so this is, you can consider as if another advantage. Suppose if you want to make only E-alkene, then you don't have to worry about whether it is stable phosphorus product or not, because if it is original Wittig reaction, then whether you have taken stable phosphorus ylide or unstable phosphorus halide. Depending on that, you can get E-alkene or Z-alkene. But in this case, that problem will not arise. You will always get E-alkene. Now the second modification, this is completely different. The first one, it is complete. Next modification is Schlosser modification. So in this modification also we are taking the phosphorus halide that you have already seen. So nothing new in the reaction partner, but we will add some extra reagent. That is the difference. And what is the purpose of this modification? It allows selective formation of E-alkene. And how it will do so? Through the use of excess lithium salt during the addition step of the halide. So halide is already present. You can also write it in this form, PPH3+, that is in polar form also you can write. Now it will be carbonyl nature. And after that, deprotonation, protonation steps are also there, which is something new that we have not seen in case of original Wittig. So here the mechanism that you are seeing, this is just simple mechanism. It will attack this carbon and oxygen will attack phosphorus. So now we will get this type of 4-membered ring, and it is called oxaphosphetane. Now depending on whether the halide is stable or not, you will get Z or E. So in this case, you can say that this halide is not stable because here carbonyl, it is attached to R group, that is alkyl group. So it is not electron withdrawing group. It will not stabilize it. So mostly you will get Z alkene. This is Z. Both the R groups are on the same side, hydrogen on the same side. So you are getting Z. But suppose if you want to get E alkene only, but you are not using any stable halide, then also it is possible. And how? Now we will use some lithium salt. So why we are using it, that you will see. We have taken lithium bromide. You can take any other halide also, lithium chloride like that. And this lithium bromide, now what it is doing, this is oxaphosphetane, right? And this is betaine. So this betaine intermediate will be stable because now lithium plus is attached to O minus. Okay. So now there is negative charge over oxygen and positive charge over phosphorus. So this bond is basically broken, and this type of betaine intermediate, now it is stable because of this lithium bromide reagent. So here lithium catalyzes oxaphosphetane opening. So this is oxaphosphetane. This, suppose I am giving the name A. A is oxaphosphetane. It is now open, thus stabilizing betaine intermediate. So betaine intermediate B, this is B. Fine. So this is the purpose. And what will be, that is, what is the benefit behind this process? That is, OP bond is broken. So what will happen now? Now see, next we are using some strong base. It is not necessary you have to use PHLI, but here we are using PHLI. But the purpose is here we need some strong base. Now this stable lithiobetaine is basically this B compound. Now it will be deprotonated. So this hydrogen, it will be removed by pH minus. So it is basically pH minus Li plus. As Li is attached with pH, it will act as base. Okay. So pH minus, it will capture this hydrogen, and as a result, there will be negative charge generation. That means now we will get carbonyl. Now when we are getting carbonyl, what is the benefit? Now the benefit is here R prime and R both are on the same side, but now bond rotation is possible, and as a result this R group, it can move towards this side. Okay, and see, this type of equilibrium will be there, and look at this equilibrium sign. It will be mostly remaining in this form where two R groups are on the opposite sides because it is more stable. So this type of bond rotation is possible only when this OP bond is broken, because if OP bond is broken, rotation is not possible. So LiBr is helping us to open this OP bond and to increase the stability of betaine, where O is carrying negative charge, phosphorus is carrying positive charge. Now when R groups are now after rotation on the opposite side, negative charge will be on this side. So here basically this deprotonation, it is actually the loss of stereogenic center, right? Because here we have one stereogenic center, but now it is after rotating this deprotonation. Deprotonation means this step is deprotonation where we are using PHLI. So deprotonation is basically helping us, as it is equivalent to loss of stereogenic center because of this type of rotation of bond. Okay, so this is the purpose why we are using LIBR, and after that we are using some strong base like PHLI. Next, what we are doing now, we will do protonation. Look here what is written, first deprotonation then protonation. So and for protonation we are using this type of sterically hindered proton donor. So this is actually tertiary butanol. This is the tertiary group and this is tertiary butanol. Use of a sterically hindered proton donor will lead to trans-lithiobutane. So this hydrogen, it is basically this one. So this hydrogen, it will be attached to this carbonyl, and ultimately what we are getting? We are getting trans-lithiobutane because this is actually butane. See here we have written B, which is also butane, but what is the difference between these two butane? Now it is trans-lithiobutane. Okay, so suppose it is B prime. So trans-lithiobutane, because here R and R prime both are on the opposite side. This is not R, this is R. So that is the purpose of using this proton donor. And finally what will happen? Next we are using potassium tertiary butoxide, and the purpose of it is that if we are using this type of salt, now Li plus and Br minus, that will be removed and OP bond formation is possible again. Okay, so oxa, we are again getting oxaphosphetane, so it is analog of A, but the difference is now R groups are on the opposite side, so I am giving it name A prime. Okay, so this O minus, it can capture this lithium plus, and K plus that can capture this Br minus. As a result, both these counter ions are now consumed and OP bond formation is possible. So we are getting oxaphosphetane again, and finally the alkene that we are getting, this is E-alkene, because R prime groups are on the opposite side. So this is known as Schlosser modification, where by using a excess lithium salt, though you can see from the mechanism not just LIBR, here we have also used some strong base. After that sterically hindered proton donor, which is tertiary butanol. After that we are also using this type of sterically hindered salt. Okay, this is potassium tertiary butoxide. So I hope the purpose of using all these reagents, it is clear, and how they are doing the modification in the original Wittig reaction, and this is known as Schlosser modification. Okay, so this video is all about modification of the Wittig, but this is not the end of Wittig. In the next video also we will discuss something more about Wittig. Mostly it will be problems and applications of this reaction. If you find this video helpful, please like, share and subscribe. I will meet you in the next video. Thank you for your time.